I am Donna Young, and this presentation is an overview of the content and the resources for the National Science Olympiad Astronomy competition that will take place at Wright State University in Dayton, Ohio on May 19th and 20th, 2017. The content focus for 2017 for the astronomy event is stellar evolution and Type Ia supernova events. This event, as well as the B Division Reach for the Stars event, both space science events, are supported by the NASA Astrophysics Division and their STEM outreach education, which now has a partnership through the Chandra mission and National Science Olympiad organization. And as you know, the Chandra website has always sponsored these webinars and posted these webinars, and they will be posted to the Chandra website again this year, earlier than usual. Hopefully, we're recording these webinars much earlier than we normally do, so hopefully they will be ready by the time that teams go back to school and start the preparation for the 2017 competition. On the Chandra website, under the education menu, there are classroom-ready materials, and then it says Science Olympiad webinars, and this is where they are posted. As well as the webinars, there is also a transcript that will be available to be downloaded as well for the people who might have auditory difficulties and want to see what I say with each slide in text form. And the PowerPoint itself that supports this presentation, the webinar, will be posted on the National Science Olympiad website. And the slides, each one of the slides, or most of the slides, have notes added to them to take you to links and URLs of where the most benefit to you, I think, for content, to get a general idea of the content for each, for instance, of the deep sky objects. The event description has not changed over time. Students will simply demonstrate an understanding of stellar evolution that is involved with Type Ia supernova events. The team of 2 takes approximately 50 minutes. We still have the same resources that you can bring. Each team is permitted to bring either 2 laptops or 1 laptop and 1 3-ring binder, or 2 3-ring binders. Again, when we say laptop, computer, any mobile device, if you bring an iPad or a tablet, that's perfectly acceptable also. The only rule is that you cannot access the internet. And we only add this to our event description because we allow computers to be used in our competition, but that is a general rule overall for all Science Olympiad events. There is no internet access unless the event is specifically written to use the internet for some particular reason. So, as you can see, we have the usual suspects in the event description. The same kinds of information, the physical properties of stars, HI diagrams, spectra, all of those properties and characteristics of stars that are basic to stellar evolution across the board. But we also have a few different things in here this year also. Since we are focusing on Type Ia supernova events, obviously we have red giants, white dwarfs. You will notice it says oxygen and helium. There are differing types of white dwarfs. We've never gotten into that before, but we are going to a little bit in the 2017 competition. Neutron stars, you will know very little about neutron stars, but I put this in here for a reason, because it is a possibility to create a neutron star from coalescing white dwarfs, so that's why I added it to the slate of content. The AM-CVN systems, though, is brand new. That is a type of variable star cataclysmic system that we have not encountered before in a previous competition. Dwarf novas, we've had a little bit in the past, but it's been several years since they have been there. And Mira variable stars are have been a part of just about every competition we've had, except for the ones involving exoplanets. And globular clusters are also there too for various and sundry reasons, as you will see as we go through the content a little bit. So the motion laws this year, the motion relationships and mathematical equations, again, have not changed. We still have Kepler's laws because to have a Type 1a supernova event, you have to have a binary system. So we have Kepler's laws of motions within binary systems. And again, parallax and spectroscopic parallax, the distance modulus again, and this year we have added in Hubble's law also. And we have 16 deep sky objects that I am going to give you a brief overview of those topics and why they are part of this current coming up year's competition. I have grouped the deep sky objects into various categories, and you will see that we have 4 planetary nebulas. We have 3 binary systems with white dwarfs. We have 2 AM-CVN systems. We have 4 Type 1a supernova remnants, and we have 2 globular clusters. One note to bear in mind when you do a search for 2 of those planetary nebulas, the ones that says Hines 2-248 and Hines 3-1357, if that's the catalog name, Hines. The shortened catalog abbreviation name is HEN, H-E-N. If you do a search for HEN 2-248, a lot of interesting things will come up, none of them astronomical in nature, so please make sure that you use the entire full catalog name number of Hines 2-248 if you want to get what you're actually looking for. So everything that's on this list has to do with items, stars, products, situations, scenarios that are going to lead to eventually, possibly, one possibility anyway, a Type 1a supernova event. Here is our usual schematic of stellar evolution that all of you must be able to dream this in your sleep without even thinking about it anymore, because it's been in every presentation that I've done since the beginning of time, I think. This year, though, we are focusing on one very small part of this stellar evolutionary sequences, and that is, of course, the stars that are sort of between 0.8 and 8 solar masses, because these size stars, as they evolve through their red giant stage and collapse into a white dwarf and produce a planetary nebula. And of course, we need that white dwarf for the Type 1a supernova event to happen. And so that is the part of the stellar journey that we are focusing on for 2017. Here is a composite of all kinds of planetary nebulas that have been observed. And you will see that they are all different sizes, and those sizes are sort of misleading in a lot of ways. They're not actually to scale because they're more like the sizes that we actually observe. When we image them, they do not take into account distances. And within this, there is a link on this PowerPoint slide to take you to this graphic, and it gives you the name for every single one of the planetary nebulas that are in this graphic. And 4 of them actually are in our deep sky object list, either directly or indirectly. The first one is the Eskimo Nebula. We have that one. And then NGC 2440 is one of our deep sky objects. The Stingray in that tiny little object is also, again, very misleading because it's much, much larger than that, actually, than it appears to be. And the 4th one is Pierce 1, which is indirectly a deep sky object because it's inside one of our globular cluster deep sky objects. So the first deep sky object that you need to be knowledgeable about is NGC 2392, which is commonly referred to as the Eskimo Nebula. This is a Hubble and composite image with Chandra X-ray observational data. Here is what it looks like in X-ray only. And here again is a composite with Hubble. It is a very strange looking nebula. It has a very complex and not well understood symmetry to it. It is only about 3,000 light years away. It's only about 10,000 years old. Planetary nebulas there are only about 10,000 of them in total, and they only last about 50,000 years before the material in the planetary nebula spreads out through the interstellar medium, gets more tenuous and thinner over time until you simply cannot see it anymore and leaves the white dwarf stellar core behind. So this particular one, it is thought maybe that the complexity of the nebula is due to a so far undetected companion star to the white dwarf stellar core, and that might be why. The white dwarf itself has a surface temperature of about 50,000 Celsius, and the winds that are being created, maybe by the interaction between the white dwarf and the companion star, are creating 6 million an hour winds that are being driven through the debris at the edges of the nebula.